Welcome to this explainer. Modern ships routinely sail with what's called unattended machinery spaces. That means literally nobody is standing in the engine room, sometimes for the entire night. How is that even possible? Well, it's because these giant vessels function almost like living organisms. They have a highly advanced mechanical nervous system, making thousands of tiny corrective decisions every single hour, faster and way more consistently than any human watchkeeper ever could. Today, we're exploring marine instrumentation and control to figure out exactly how the ship thinks.
0. That's the actual number of humans down there at night on a vessel operating with unattended machinery spaces. Just imagine that for a second. You've got thousands of tons of steel, roaring diesel engines, high-pressure steam boilers, all just hurtling through the pitch black of the ocean, and literally nobody is in the engine room. It's wild, right? But it works seamlessly because of a vast, invisible network of sensors and control loops quietly running the shell.
Okay, Section 1, the unattended engine room. Let's dive right into this.
To really grasp how zero humans can safely operate something this sprawling, we kind of have to frame the sheer scale of the problem. A ship just has way too many simultaneous processes going on for anyone to manually adjust everything. I mean, think about boiler levels, cooling water temps, cargo tank pressures. It's a humanly impossible problem to manage manually. That's where our nerves come in, instrumentation. These devices continuously measure physical conditions. Take a Venturi tube, for example. It measures flow by creating this deliberate narrowing in a pipe, which causes a predictable pressure drop. Measure that drop and you get the flow rate without any moving parts. The goal here isn't just to put a number on a screen, it's to feed real-time data into a system that automatically nudges equipment, like valves or dampers, to hold a process exactly where we want it.
So, what do these nerve endings actually look like? Well, the ship senses its environment primarily through three main types of devices. We've got the Borden tube, the thermocouple, and the bimetallic strip.
What's absolutely brilliant about these is the physical mechanics behind them. They translate environmental changes into readable data instantly, without needing some complex computer right at the source. For instance, a Borden tube is basically a curved, flattened tube. When internal pressure builds up, it physically tries to straighten out, and that straightening moves a pointer. Pretty neat, right? Then you have thermocouples. They use two dissimilar metals joined together, and when they heat up, they generate this tiny, totally predictable electrical voltage. And a bimetallic strip? It literally bonds two metals with different expansion rates. As it warms up, the whole strip physically bends. It's just elegant physics in action.
Moving on to Section 2, the basic control loop.
Okay, so we've got our individual sensors. But look, a nerve is pretty useless if it doesn't trigger a muscle, right? I absolutely love this analogy. A control loop is just a constant conversation. The ship is continuously talking to itself. It senses the real-time conditions, compares them to what's supposed to be happening, and then physically makes an adjustment. And it repeats this conversation continuously, forever, totally automatically.
Let's walk through how that conversation plays out structurally. Step 1 is the transmitter. This takes the sensor data and says, hey, here is what's actually happening right now. Step 2 is the comparator. This checks reality against your desired set point and says, okay, here is how far off we are. And finally, Step 3, the correcting unit. This is the muscle, the valve turning or the actuator pushing that says, all right, here is the physical correction we need to make. And then boom, it loops right back around to the transmitter to see if that correction actually worked.
Which brings us to Section 3, Mastering PID Control.
So we've got the nerves and we've got the reflexes. Let's look at the actual brain of the operation. This shows exactly why simple reflexes just aren't enough for heavy machinery. If we use a purely proportional response, meaning we just correct based on how far off we currently are, the system tends to overshoot the target. It'll oscillate and eventually settle, but slightly off the mark. It leaves this annoying steady-state offset. But when we upgrade to full P plus I plus D control, proportional, integral, and derivative, the system settles down quickly, stably, and precisely dead on target.
The real secret sauce here, the thing most people miss, is that integral term. I like to think of integral action as a highly patient, incredibly meticulous worker. Because proportional-only control almost always leaves that slight offset, the integral component's specific job is to accumulate a tiny, continuous nudge over time. It just keeps pushing and pushing until that very last bit of steady-state error is squeezed out completely.
And here is the math that actually makes it happen. Now, please don't let this equation freak you out. What you're seeing here is literally just the formula that calculates the final output signal.
The Kp, Ki, and Kd are just tuning knobs for our proportional, integral, and derivative actions. All this fancy calculus ultimately just calculates a simple physical instruction, like telling a valve to open to exactly 42% to keep the ship's cooling water perfectly stable. That's it.
All right, let's hit Section 4, Managing Shrink and Swell.
Let's apply this to a real-world scenario where a basic control loop can actually get totally tricked. You really need some advanced logic here. So pause for a second and put on your control engineer hat. Imagine a massive, high-pressure boiler on the ship. Suddenly, the ship's engine demands a huge, rapid increase in steam. What do you think happens to the water level inside that boiler drum in those first few seconds?
Well, the textbook answer is completely counterintuitive. When that steam demand spikes, the pressure in the drum briefly drops, and that pressure drop causes the existing steam bubbles, the ones suspended inside the boiling water, to rapidly expand. The swell pushes the apparent water level up, even though the actual total mass of water hasn't changed at all. So if you had a simple single-sensor control loop, it would look at that rising water level, completely panic, and wrongly shut off the incoming feed water at the exact moment the boiler desperately needs more water to replace the steam it's losing.
To stop the controller from chasing that false reading, engineers use what's called three-element boiler control. Instead of just looking at the drum level, the system simultaneously monitors the steam flow leaving the boiler and the feed water flow entering it. By combining these three elements, the brain essentially anticipates the disturbance. It sees that steam demand spike and knows, hey, we need to add water right now, crash-checking the data and completely ignoring that temporary swell effect.
Okay, final part. Section 5. Advanced Control and Safety. As we've seen, individual loops can be super sophisticated, but to run an entire ship, these loops have to talk to each other. To manage all these interacting systems, we use cascade control. The best analogy for this is like taking a shower with two knobs. In cascade control, the output of an outer loop automatically becomes the set point for an inner loop. So the fast-acting inner loop instantly handles quick, minor disturbances, like a sudden pressure drop in the pipes, while the slower, more patient outer loop looks at the big picture temperature and adjusts the overall target. It's a macro-level system directing a micro-level system.
Now, here is the absolutely crucial point to remember. Automation is incredible, yes, but unattended operations are strictly only as safe as the alarm system monitoring them. Think about it. When the engine room is completely empty, nobody's down there to smell an overheating bearing. Nobody's going to hear the gravelly noise of a cavitating pump or spot a tiny little oil leak. Because of that, a UMS-certified ship is required to have deeply redundant, rigorously tested alarm pads. These have to reach out of the engine room and directly alert the duty engineer. It often even includes a personal alarm system that triggers if the engineer themselves becomes incapacitated, because literally nobody else is there to notice a developing fault in real time. Which brings us to our final thought. This ship's nervous system really is a marvel of physics, math, and engineering. It's quietly taking thousands of actions per minute to keep the vessel alive. But if a sensor breaks, or a valve jams, or the nervous system completely fails, who wakes the brain? It ultimately all comes back to the human responsibility behind the automation. That lone engineer responding to an alarm in the dead of night. Definitely think about that the next time you picture a modern cargo ship crossing the ocean. Thanks for joining me on this explainer, and keep questioning how the world around you works.